So just like any other transform, we'll study the properties of the discrete Fourier transform. Some of the properties are pretty trivial, and they just follow because of the linearity and other definitions of the discrete Fourier transform. But some other properties are things that you would see for the first time, and we'll try to explain those properties in more details than other properties. So the first property, which all the transforms that you have done so far, actually, continuous time Fourier transform, Laplace transform, discrete time Fourier transform, Z transform, they have this property, and indeed DFT also has this property, which is the linearity property, which says that if Gn is a sequence and you take its DFT, now for DFT, we always have to specify how many points. So it's an n-point DFT. And then Hn is a sequence, and you compute its n-point DFT to Hk. And now someone gives you a sequence which is a linear combination of these two sequences. So alpha Gn plus beta Hn, where alpha and beta are two complex numbers. The main thing is that in this linearity property, the number of points that you are calculating must be the same. Okay? So alpha and beta Hn, if you still compute the n point, then the answer is that the DFT of this sequence will be alpha gk plus beta hk. So nothing new here. But the second property is something which is unique to the DFT. And that property is called circular time shift. Okay. Now, we know for a discrete time sequence and a DTFT what happens to the phases of the frequencies if you shift the signal. So in DTFT world, if we shift a signal xn by some amount n naught, then it results in a phase shift in the frequency domain. Now, the question is, what causes a phase shift? What operation causes a phase shift in the DTFT domain? Okay. And the operation cannot be time shift. Why? Because if you do a time shift, you are effectively, in the language of DFT, we learned about the concept of length. You are changing the length of the signal. For example, if I have a signal, length 4 signal, so I have n equal to 0, 1, 2, 3, and I say, well, let's compute x of, take this to x of n minus 1. Now I have 0, 1, 2, 3, 4. I have changed the length of my signal. I've changed the length of my signal from a length 4 signal to a length 5 signal. So in the DFT world, shifting a signal in the usual sense does not make much sense, because you may end up be in a situation where actually the length of your signal becomes bigger than the number of points of your DFT. Okay. So if I were computing a 4-point DFT, then in the next case, I'm looking at a different kind of a signal. I have now a length 5 signal. So In the DFT world, actually, the phase shift relates to something called a circular time shift. So circular time shift corresponds to the mod operation that we had learned. So circular time shift is just graphically, what circular time shift says is that if you have a signal 0, 1, 2, 2, 3, and if you want to shift it to the right by a factor of, let's say, 1, what that means is that every sequence, every value gets shifted to the right. So whatever was at 0 comes to 1, 1 goes to 2, 2 goes to 3. Now in the classical linear shift, the 3 value goes to the 4, n equal to 4. In circular shift, the 3 value wraps back and comes to 0. Okay. Similarly, if I was doing a circular time shift to the left, it will be just a reverse process. 3 will go to 2, 2 will go to 1, 1 will go to 0, and 0 will wrap back to 3. Okay. So another way of thinking of this is like two dials, right? You have two circular dials where the outer indices corresponds to the indices of your time sequence. So you have n equal to 0, n equal to 1, n equal to 2, 3, 4, 5, and let's say this is n minus 1, right? So it's a length n sequence. And the inner dial, so you also have an inner dial which corresponds to the value. So originally your value, you have here, let's say g of 0, you have g of 1 here, and you have g of 2, and you keep on going here, you have g of n minus 1. And the idea is that if you are circularly shifting to the right, you basically rotate your inner dial by the amount of your circular shift. Right? So if you rotate it by 1, G0 goes to n equal to 1. And G1 goes to n equal to 2, and so forth. Right? Or if you are circular shifting to the left, then you simply rotate your dial to the left. Now, your different books use different conventions. I prefer this convention. Doesn't matter as long as you're consistent in how you label your outer axis, your outer dial and your inner dial. Okay? So this is the concept of circular shift. Now, mathematically, that's just a mod operation. So mathematically, a circular shift is given by the mod operation. So we had talked about K mod n. K mod n is defined as smallest positive integer are such that k equals to n times another integer plus r. So the last time we had done that if k is positive, then k mod n is simply remainder of k divided by n. Okay. And if k is negative, then k mod n is simply n minus remainder of absolute value of k mod n, or you can equivalently write that as n plus remainder of k mod n. Okay. So a circular shift, if I say if I'm given a sequence, say given Gn, okay, if I want to circular shift it to the right by n naught, then the circular shift by n naught, you will define that as g of n minus n naught mod n. Okay. And similarly to the left, it will be g of n plus n naught mod n. So let's say your original indices were 0, so you have n equal to 0, 1, 2, 3, 4. Right? And you are asked to compute circular shift to the right by 2. So what are the values that you are going to get? For n equal to 0, you are looking at 0 minus 2 mod 5. So that's minus 2 mod 5. And that is going to be equal to 3 because n is 5 and remainder of minus 2 divided by 5 is minus 2. So that's 5 minus 2, that's 3. Okay. The other way you could have seen is again the graphical representation that actually 0, everything is moving by a factor of 2. So 0 is now going to 2, right? 1 is going to 3, 2 is going to 4, and 3 is going to 3 wants to go to 5, right? But you can't go above 4, so it has to go back. So it goes to 0. Okay? So basically whatever was the value, so effectively your new sequence, whatever was the value at the third index is your new value. Similarly for n equal to 1, you are looking at 1 minus 2 mod 5. That is equal to 5. So that's minus 1 mod 5, right? Which is equal to 4. And then you are looking at 2 mod minus 2 mod 5, that's 0 mod 5, that is 0. Okay. 3 minus 2 mod 5, that's 1 mod 5, that's 1. 4 minus 2 mod 5, that's 2 mod 5, and that is 2. So if your original signal was, let's say, 0, 1, 2, 3, and 4, right? If this was your Gn, G of n minus 2 mod 5 is going to be whatever at 0 now you have what was at 3. So you will get this. Then effectively everything is going to the right by a factor of 2. This is going here. 1 is going to 3. 2 is going to 4. And 3 is going to 0. And 4 is going to 1. So you'll get 0, 1. Then you have again 1, minus 1, 1. So this is 2, this is 3, and this is 4. Okay. So this is this is G of n minus 2 mod 5. Okay. So this is called the circular shift. You can do it for the left too, you'll get a new sequence. So once we understand the concept of circular shift, then we have a similar formula to what we did in DTFT, which is that in DTFT, linear shift in time means phase shift in frequency. In the DFT world, circular shift in time. So if I take a signal and if I shift it in time by n naught, circular shift it by n naught, and this capital N has to correspond to the number of points of my DFT, then that is equivalent to doing a phase shift with this, which is given by which is given by k n naught times g of k. Okay. So it's e to the minus j 2 pi k n naught over n g of k, which means that your original DFT, each index get a phase shift of minus 2 pi k n naught over capital N. Okay. In the DFT world, we used to have that so in the DTFT world, right, we had that n minus n naught, the DFT is e to the minus j omega n naught g of e to the j omega. So it's very similar, but you need a circular shift for that to happen. You cannot have it with a plain linear shift. The third property is the circular frequency shift. And again, the idea is very similar to what we have in the discrete time Fourier transform world, which is that if we modulate our time domain signal, so if you have Gn, and if you modulate it by a frequency, in the DTFT world, that corresponds to shift in frequency. Now, in the DFT world, once again, instead of a linear shift, what we will have is a circular shift in indices. So we'll have k minus k naught mod n. Okay. Which is exactly the same operation that if you are looking at your DFT plot, what will happen is that your DFT plot will simply, the values will get circularly shifted and some of the n indices will come back at the start if you are doing right shift. Right? So depending upon the frequency that you are modulating your signal with. The next property is duality, which says that if Gn, its endpoint DFT, is Gk, and now you have a time domain signal whose values are exactly the same as the DFT of your original signal. Okay? And if you compute its endpoint DFT, then that will be equal to n times g of minus k mod n. Okay. Now, minus k mod n is a very simple operation. So what this means is that this will be equal to n g of n minus k for k not equal to 0, and this will be equal to n g of 0 for k equal to 0. So this is analogous to what we talk about in the discrete time Fourier transform world. One of the common things, the duality principle there is, like we say, the Fourier transform of a box signal is a sinc, and the Fourier transform of a sinc signal is box. The only thing is that you have some relative scaling. Right? This is very similar aspect, but now the duality includes that circular shift operation. So the shape is almost the same with some circular shift. Okay. If you are given a sequence, time domain sequence, you compute its DFT, or if you are given a time domain sequence whose signal is very similar to the DFT of the first sequence, the DFT of that sequence will be just like the original signal, but with some small circular shift. Okay. Okay, the next property, which is the most important property that you should know about, is called circular convolution. And this property, if you remember, we talked about at the start that there are two main reasons of using DFT. One reason is that it helps us do spectral analysis. We talked about that earlier. The other reason of using DFT is that it helps us do processing of discrete time systems in a much faster fashion. What happens is, if you look at convolution operation, if you want to convolve two signals using the convolution sum, it can take a very long time for long signals. But you can use DFT to compute linear convolution in a very fast fashion because of the fact that DFT has a very fast implementation using the SFT algorithms. Now, this circular convolution property of DFT is what helps us do that. Circular convolution is related to linear convolution, and that's what we need to understand. What is the relationship and what is the property? Okay. So the goal is that we want to use this property eventually to do discrete time processing of signals. In particular, we want to really compute linear convolutions very fast. So what is circular convolution? It is defined between two signals of equal length. Now, if they are not the same length, then we know how to make them same length. Right? You will take the smaller length sequence and you will zero pad it. So possibly zero pad it. I am going to ignore the aspect of zero padding because that's now pretty fundamental to our understanding of DFT. So without loss of generality, we'll say that we are given two sequences Gn and Hn of length n each. Now, in linear convolution, we know that, so linear convolution is, let's say we are interested in computing linear convolution yn equals to Gn convolved with Hn. That is simply m from minus infinity to infinity, Gm h of n minus m. And since G is length n, I can just write that as m from 0 to n minus 1 Gm h of n minus m. Okay. Now, the linear convolution of two sequences is of length. The length of linear convolution is bigger than the length of either one of those two sequences. In particular, the length of this linear convolution will be 2n minus 1. Right? Length of one sequence plus the other sequence minus 1. So n will go from 0 to 2n minus 2. And the way to think of linear convolution is, so linear convolution involves you fix one sequence, any one sequence, doesn't matter. You flip the other sequence, and then you add them all up, and you after the shift, which is proportional to the little n that you are after. Right? So you flip and then you shift or slide. Right? So you slide by n. Okay. Now in circular convolution, the operation is almost the same. The goal in circular convolution is you want to circularly convolve two sequences so that you get back a sequence of the same length as the two original sequences. So circular convolution, if you start with two length n sequences, you get back a length n sequence. So circular convolution is fundamentally different from linear convolution in the sense that circular convolution gives us back a length n sequence again. Now, fundamentally, circular convolution is actually associated with some length n, because if you have finite duration sequences, if two sequences are length 3, I can always say compute their 10-point circular convolution. So the notation that is used for circular convolution, there are many notations. One notation that is used is Gn, convolution symbol with the circle around, Hn. But this notation is ambiguous because it doesn't tell you what is the length of the circular convolution. So sometimes people also write, which is what your book uses, Hn, or some people simply put the n on top of this circular convolution symbol. So the output of this thing is always from 0 to n minus 1, where n is the number of points of your circular convolution. So for these finite sequences, how is the circular convolution then different from linear convolution? Well, the first part is the same. You take one sequence, and just like the linear convolution, circular convolution is commutative, so you can change the order of what you do with one sequence. So we'll stick with the previous version, which is that you fix one sequence, so Gm, and the summation thing still remains the same, n minus 1. Now, the difference that comes is that in linear convolution, you flip in a linear fashion, and then you shift in a linear fashion. So instead of Hn minus m, in circular convolution, what you write is n minus m mod n. And the way to interpret that is, if you first look at it, h of minus m mod n, right, you should call that a circular flip. So instead of a linear flip, you are doing a circular flip. Okay? Now, if you remember your mod operation, the circular flip is defined as it is 0 for m equal to 0, and it is n minus m for m not equal to 0. If you want to mathematically think of, if you want to graphically think of circular flip, what it is that, so you start with indices, let's say 0, 1, 2, and 3, and you have three values, h0, h1, h2, and h3. Okay, circular flip basically says that you fix the value at h0 just like in the linear case, but now you sort of change the order of your rest of the indices. Okay, so it will be easier for me to actually do it this way, that I make this index now 3. So I start with here. I make this index 1, 2, and 3. So instead of doing the indices in one way, either clockwise or counterclockwise, I do it the other way around. Okay? But 0 is fixed. So of course, at the end of the day, you still have a length n sequence left with you. So if my age was, for example, let's say 2, so this is the index n, 1, index 2, this is -2, this is 1, and this is -3 at index 3. Right? So if this was my age of n, a flipped version of that, age of -n mod 4, or age of -m, doesn't matter, it's just a dummy variable. Right? At 0, we still have the same value, n equal to 0 will have 2, but now we'll start putting down values while going this way. Okay? So at index 1, I will have the value actually -3. Let me go down. -3. At index 2, I'll have the value -2. And in index 3, I will have the value 1. Okay. So just like the flip version, linear flip, where you fix n equal to 0 and then you take it all the way back, here it's just you are doing a circular flip. So what circular convolution, which is this formula here, is telling you is you fix one sequence, then you circularly flip the other, and then you do a circular shift. Okay, so how is that related? You have basically what the formula says is n minus m mod 4. That I can write as age of minus m minus n mod 4. So what is this minus? So this is the circular flip version. Sorry, the minus should be inside. This is minus m minus n mod 4. So what this is saying is you circularly first flip your signal, and then you are shifting your resulting signal by a factor of n. Okay, so very similar to the linear shift version, except that now instead of this n minus m, you have n minus m mod 4. So let's then interpret it, what it is saying, or how do you calculate different values of your circular convolution. So of course y0 is simply equal to m from 0 to n minus 1 g of m h of minus m mod n. Okay. So what this says is that, of course, this is a length-n sequence. Okay. And this is a length-n sequence because when you circularly flip a sequence, you still get back the same length sequence. And after that, you do pointwise multiplication of the two sequences, and then you add them all up. For example, so I'll work with the same example, h of n. So let's say my g of n was 1, 0, 0, minus 1. 0, 1, 2, and this is the index 3. So once I have circularly flipped my signal, what the 0th value of the circular convolution is, I just do the usual thing. I do linear convolution. I multiply point by point and then add them all up. So so for this particular thing, I have m from 0 to 3. I do G0 and then this value, so I have 2. I get 1 times 2 plus 0 times minus 3 plus 0 times minus 2 plus minus 1 times 1. And the answer I get is, sorry, I should get rid of this summation because I'm just writing all the terms individually. So the answer I get is 2 minus 1 equal to 1. Now, what is y1? y1 is simply m from 0 to n minus 1, g of m, h of minus m, 1 minus m, mod n. So in this particular example, where n is 4, that is equal to m equal to 0 to n minus 1, g of m, h of 1 minus m mod 4. So you can calculate this 1 minus m mod 4 by hand because we know the mod formula. But here is the simple thing. Once you have this circular flipped version, right? I can write it as minus m just to make it simpler. It's just a dummy variable. I'm now looking at 1 minus m, which is equal to minus m minus 1. So I am looking at this using this circularly flipped version and just circularly shifting it to the right by 1. So from my original hn, I have gotten to this point, and after I am at this point, all I have to do is do a circular shift to the right by 1, which means that I move every value to the right. So 2 comes at index 1, minus 3 comes at index 2, minus 2 goes at index 3, and 1, where does 1 go? Back to 0. Right? So if I were to plot that h of 1 minus m mod 4 is going to look like, I will have at index, so these are my indices, 1, 0, 1, 2, 3. 2 is going to come at 1. And minus 3 is going to go at 2. So I'll have here minus 3. And then minus 2 is going to go at 3. So I have here minus 2. And then 1 is going to go at 0. Okay. Of course, my stems are not according to scale. Let's make this a little bigger. And after that, all I have to do is again the same thing. I multiply this. I am fixing Gn in this example. Right? So my Gn always remains fixed. I can just make it Gm just to change the index, but it's the same is the same signal. So again, to calculate y1, I just do point by point multiplication and then add them all up. So if I do that, what I'm getting is 1 times 1 plus 0 times 2 plus 0 times minus 3 plus minus 1 times minus 2, which is 1 plus 2 equals 3. So that is my value of circular convolution for n equal to 1. And similarly, I can do that. I can go to y of 2. Now I won't write the expression again, but it's the same trick. I just have to work with this version. I now shift it one more to the right, because for y2 I need 2 minus m mod 4, which I can simply get by shifting everything to the right. So 1 goes to index 1, 2 goes to index 2, minus 3 goes to index 3, and minus 2 goes to index 0. So I get 1 at index 2, so 0, 1, 2, 3. 1 goes at index 1, 2 goes at index 2, minus 3 goes at index 3, and minus 2 goes at index 0. And now I just multiply this with my original gm or gn. And the value I get is 1 times minus 2 plus 0 times 1 plus 0 times 2 plus minus 1 times minus 3. So that's minus 2 plus 3. So that's 1. Okay. And of course, I have to go up to yn minus 1. In this example, n minus 1 is 3. So the final version is y3. Again, for that, I just go from this to h of 3 minus m mod 4, which again is just shift everything to the right, and at this, you bring it back to 0. So the signal that will look like is minus 2 goes at 1, 1 goes to 2, and then the value 2 goes to 3, and minus 3 goes to 0. And now I just add all the things up, y1, so this is my g0 times minus 3, plus, of course, I'm multiplying g1 and g2 are 0, so I'm just going to write 0, plus g3 is minus 1 times 2, so that's minus 3 minus 2, that's minus 5. And you could, of course, do it for any value of capital N. The main thing to remember is that just like if you remember your flip and slide rule for linear convolution, then circular convolution is very similar to that. You have circular flip and circular slide. And as long as you know the meaning of circular flip or circular shift, or you remember your mod formula, after you do the flip, it's very simple. You just keep on doing one circular shift at a time. So you can, for circular convolution, you can either use the formula directly, you can compute the mod operation, you can use this graphical representation, or you can use a tabular way of computing the circular convolution. So here is the tabular method. Again, I'm going to give you an example using this n equal to 4 case. Okay? So the way tabular method works is You are interested in computing the circular convolution for n. So you have n that goes from 0, 1, 2, 3. Right? These are the values that you are interested in computing. Now, the circular convolution formula says fix one sequence. Okay, so I'm going to fix G as fixed. So I write G0, G1, G2, G3. Okay, so this is m equal to 0, m equal to 1, m equal to 2, m equal to 3. Right? Of course, if I have more, I keep on going down. Now, for n equal to 0, this is the only thing you have to write. You have to do the circular flip. So what is circular flip? For m equal to 0, it is h0. So we keep at index 0, we keep it fixed, and then we start counting backward, right? So we then write h3, h2, and h1, right? So this is the first value is always h0, and the second one will be hn minus 1, and then you keep on going down till h1. Okay. Now, the tabular method says that you basically, so for every n, this g will always be fixed. So g0, g1, g2, and g3. Doesn't matter which n you are using, that will always be fixed. Now what will change is that as you go from one column to the other, you want to shift this H sequence one row down. Okay. And then for the last one, since it cannot go down, it goes back up. So what you have is H0, H1, H3, H2, and then H1 cannot go down, so it's H1. So this is just a tabular way of just showing what the circular convolution, the graphical thing we wrote. Okay. Similarly, you just bring it one row down. So that will be H1, H0, H3, and H2 goes up. Similarly, you do that for the last case. So you get H2, H1, H0, and H3. Okay. And once you have done that, basically Y0 is simply equal to, you add all these rows up. You multiply. So this is, each row is a multiplication operation. You add them all up. Y1 you do for this column, Y2 you do for this column, and Y3 you do for this column. Okay. So any one of these methods, the main idea is that you are fixing one sequence, you are circularly flipping the other, and then for every n, you are starting from that circularly flipped version and circularly shifting it to the right by one. Okay, so we discussed circular convolution because we were really interested in doing the convolution property of DFT. As we discussed earlier, in the DTFT world, if you linearly convolve two sequences, that is equal to multiplication of their DTFTs. Now in the DFT world, the theorem changes, and you will see that as a pattern that everything that has linear stuff in DTFT ends up having this circular relationship in DFT. Okay? So the theorem is that if you circularly convolve two sequences, okay, so you have endpoint circular convolution and you compute their endpoint DFTs, you ask what is the DFT of the circular convolved output, right? that is equal to the multiplication of their respective endpoint DFTs. Okay. So you have this convolution equals multiplication theorem, but now you are not doing linear convolution. Whenever you are talking about DFT, you are doing circular convolution. Just like when you talk about DFT, you don't talk about linear shift, you talk about circular shift. Now, this theorem is one of the most important theorems in terms of using DFT for processing. And here is the reason that this theorem can be used to compute circular convolution in a very fast manner. And why is that? Because if I was given two length n sequences, so cost of circular convolution is quote unquote high. Because if you look at the circular convolution formula, m from 0 to n minus 1 gm h of n minus m mod n and n goes from 0 up to n minus 1. So what are you doing in each circular convolution? For each point you are doing n multiplications and n minus 1 additions. It's very similar to the cost that we looked at for computing DFT using direct formula, right? So for each n, there are n multiplications and n minus 1 additions. It means the total cost is you have n values, so that's n squared multiplications and n squared minus n additions. Okay. That's high for the same reason we talked about computing DFT directly is costly. But what this formula says is that I can take my sequence Gn, okay, and I can compute its endpoint DFT HK using only order n log n to the base 2 operations. So it's GK. Now, why can I compute DFT in such a fast manner? DFT can be computed using FFT, which is an algorithm, and using that algorithm, we can compute it in a very fast fashion. So I can do that. Then similarly, I can take my sequence HN. I can compute its endpoint DFT to get HK, right? And the cost of that is also order n log n to the base 2. Right? And then this formula says that let's multiply them together. So that's n multiplications. Okay. And then I compute an endpoint inverse DFT. So I multiply, I get GKHK. I get an endpoint inverse DFT, and what I should get is indeed Yn by this formula. Now, what is the cost of this endpoint inverse DFT? It is also order n log n to the base 2 because you can use again FFT or inverse FFT. So the total cost is whatever was the constant here, it still is some constant times n log n to the base 2, okay, which is depending upon the value of this constant and depending upon n, this can be much smaller than n squared. Okay. So circular convolution and this formula is one of the fundamental things using FFT. All these things come together to help us compute eventually, which we'll see, linear convolution in a very fast manner. But we'll come to that later. Okay, so the next theorem we want to do is the modulation theorem, which again you will notice the similarity with the DTFT world. So what is the modulation theorem? You are given a signal, let's say Hn, and you modulate it with another signal Gn. Okay. In the DTFT world, that is equal to convolution in DTFT domain. It's 1 over 2 pi convolution of one's DTFT with the other DTFT. Now, by now, you guys should be experts in the fact that if you in the DFT world, you are not just going to get convolution, you are going to get circular convolution. So what you will get is circular convolution of their respective DFTs. And the final theorem, Parseval's theorem, is that energy in one domain is proportional to the energy in the other domain. It's like the law of conservation of energy principle. So if I calculate the energy of my time domain signal, that is equal to the energy in the frequency domain and scaled by 1 over n factor. Okay. So this is total energy in time equals 1 over n times total energy in DFT domain. Okay. Now this Parseval's theorem pretty much holds similar variants of that for any orthogonal transform. In particular, I talked about it during the definition of DFT that some books like to have, instead of the DFT formula where the forward equation has no 1 over factor, and some books replace that with 1 over square root of n, and the inverse formula they replace 1 over n with 1 over square root of n also. That makes the DFT transform orthonormal, and what that does is that in that case the Parseval's theorem, this 1 over n goes away. Okay, so some books prefer that because it says that energy in time is exactly equal to the energy in the DFT domain. But in that case, as we talked about earlier, the interpretation of DFT with DTFT introduces a scaling factor. So you gain some, you lose some.